Hello everybody, welcome to Lab 6 of Artificial Intelligence. This Lab 6 focuses on constraint satisfaction problem. So let's try understanding the constraint satisfaction problem before you go ahead with the pre-lab and other things. The constraint satisfaction problem is a powerful representation for the such problems. So the constraint satisfaction normally is defined by three variables. One is x, which is a set of n variables x1, x2 and so on. D is a set of domains d1, d2, dn and so on, one for each variable of xi. And C is a set of constraints c1, c2 and so on, ca. Each constraint, this is important over here, each constraint ci consists of a pair, scope and relation. This REL stands for relation, where scope is a tuple of variables that participate in the constraint, and relation is a relation, REL is a relation that defines the values that those variables can take on. A relation can be represented as an explicit list of all tuples of values that satisfy the constraint, or as an abstract relation that supports two operations: testing if a tuple is a member of the relation and enumerating the members of the relation. So based on this, the final solution is an assignment of values to the variables that satisfy all the constraints. So the goal of this constraint satisfaction problem is, given a set of values which based on the domain, we need to find out all the solutions that satisfies the set of constraints. So that's the basic objective of constraint satisfaction problem. This is the pre-lab which you ought to have done it. Solve the CSP problem. 2TWO plus TWO is equal to FOUR. Do not simply read it as 2 plus 2 is equal to 4. So your objective is to find the values for T, W, O, add this TWO to TWO and find the values of F, U, R, and where OL is already defined over here. So that's the constraint over here. So your goal is to find the values for the variables T, W, O, F, U, R. Satisfying the constraint TWO plus TWO is equal to FOUR. So you need to identify all the possible solutions. This is one pre-lab. And the second pre-lab depends on arc consistency. This is also a variation of a constraint satisfaction problem. A variable in a constraint satisfaction problem is arc consistent if every value in its domain satisfies the variable's binary constraints. Here we use the word binary. Binary means a one-to-one relationship which consists of two values. More formally, xi is arc consistent with respect to another variable xj. See, here we are considering two variables xi and xj. If every value in the current domain di, this di is the domain relevant to xi, there is some value in the domain dj. This domain dj is relevant to xj that satisfies the binary constraints on the arc xi to xj. So this is the relationship. So that's a network is arc consistent if every variable is arc consistent with every other variable within a network. For example, consider the constraint y is equal to x square, where the domain of both x and y is a set of digits, that's 0 to 9. We can write this constraint explicitly as, suppose if I take up the values of y as 0, 1, 2, 3 within the limitations, that's the digits, and the x square value would be 0, 1, 4, 9. Based on the constraint, that's again the set of digits. This we call it as arc constraint. This is a variant of the constraint satisfaction problem. So the pre-lab 2 depends on the constraint, arc constraint. So you have to apply the arc constraint 1 for the following. The latest version we have is arc constraint 3. For this given network, we need to apply the arc constraint and find a solution. So you need to come prepared with these pre-labs. Coming to the in-lab, this is somewhat relevant to edge coloring or map coloring or graph coloring. See, look at the question over here. Kindly go through the question carefully. Suppose we have to color a map with different colors where no two neighboring regions can have the same color. So you need to fill colors in this. See, this is a map. You have to fill colors such that no two neighboring regions should have the same color. So we need to just paint each region of a map with a different color, and none of the regions that neighbor each other can have the same color. Let us assume that we have 5 colors: red, blue, green, yellow and pink. So your objective is you have to write an efficient Python code to color the regions given in the map. So do not go with the graphical part of it. So you have to understand the solution. You have to find a feasible solution for this. It's not actually coloring this particular map. So you need to find out for each of these states which color should you give such that no neighboring states will have the same color. See here, this is how the solution looks like. If you clearly observe this solution, this is a dictionary. For Madhya Pradesh, you give the red color. For Andhra Pradesh, you give the red color. For Kerala, you give the red color. Definitely all these 3 states will not be adjacent. If they are neighbors, we cannot be using the same color. For Odisha, it is blue color. This is how the output should look like. So this is a variant of graph coloring, or we call it as a map coloring problem. This is the problem you have to solve within the lab. So just to understand this, I have taken a small example over here of graph coloring. This is an assignment. The graph coloring is an assignment of colors to the vertices of graph. Strictly speaking, the coloring is a proper coloring if no 2 adjacent vertices have the same color. If you look at this particular graph over here, no 2 adjacent nodes have the same color. This is red, this is yellow. Again, you can go for red because this node is not adjacent to this. This is a different color, this is a different color, and all these nodes are adjacent. So in this case, 1, 2, 3, 4 colors have been used to map and to color the vertices. This is what graph coloring is. You need to always find out the minimum number of colors required to color the map or the graph. So this is another example. You can see the various states and union territories in India. Look at this. Here we have the green color. Here we have yellow color. If you look at it, what are the number of colors that have been used, the minimum number of colors. So as you can clearly observe from this, no 2 adjacent states of the union territories have the same color. So this is the objective of the in-lab. So in order to do this, I'll give you a small hint for this. So the process that you need to follow is, how should you consider the input? So all the colors, here the problem says we need to use these colors: red, blue, green, yellow and purple. Consider this as a list. Consider the colors as a list. What are the states given in the program? What are the various states that have been taken into consideration? Consider the states as another list, and consider the neighboring states in the dictionary and assign values. So these are the 3 inputs that you need to take into consideration. The first one is the colors as a list, the states as a list, and the neighboring states as a dictionary, and assign the respective values. So based on this dictionary, which consists of the neighboring states, we need to return a dictionary which specifies the color for each of the state. That's the output. So based on this process, you need to identify a solution and write it in the Python programming language. This is what the in-lab is. Coming to the post-lab, this is again a constraint satisfaction problem relevant to, you might be aware of the magic square, which you come across in journals or you come across in this weekly magazines. What does this magic square tell you is, you consider the sum of the rows, or you consider the sum of the columns, or you consider the sum of the diagonals. All the sum should be equal. Then only we call that matrix as a magic square. So in this, the first case, you consider the first test case. So what are the inputs? 10, 11, 12, that's the first row. The second one is 13, 14, 15, second row, 16, 17, 18. If you consider the totals, the numbers in the rows or the columns do not add up to the same value. If you consider, say, 10 plus 11, 21 plus 12, 33. So the sum of the elements in the first row is 33. Whereas if you consider this is 27 plus 15, 42. So these two sums are not equal. You need not go for the next one. So similarly, if you consider the column values 10, 13, 16, 11, 14, 17, 12, 15, 18, all the sums should be equal, then only. So the first test case fails. So consider the second test case. The values are 17, 10, 15. See here that those are organized as rows 12, 14, 16 and 13, 18, 11. Clearly observe both these inputs are list of lists for the matrix representation. If you clearly look into this, the first row sums up to 42, the second row sums to 42, the third row sums to 42. You may go with the same case for the column. The first column gives you 42, the second column gives you 42, the third column gives you 42. If you consider this principal diagonal 17 plus 14 plus 11, that ends up with 42. If you consider the second diagonal 13 plus 14 plus 15, this ends also with 42. Since all the sums are identical, equal, this matrix we call it as matrix magic square. So here the output would be true. So we need to check whether this given set of a list of lists which is organized as a matrix, whether it is a magic square or not. So your objective is to write down a Python program to satisfy this. So this is a problem which comes under the constraint satisfaction problem. Thank you, and get ready for the next lab. The pre-lab of the lab 7 you should be ready. The post-lab also of the lab 6 should also be completed before you go on for the next lab. Thank you.